Welcome to EPG Pathshala lecture series in computer science. This course is on operating systems. In this module, we learn how memory management is handled in the Linux operating system. The learning objectives for this module are to learn how memory management is done in Linux operating system with respect to physical memory, which comprises of a buddy algorithm and a slab allocator, and we will also see how the virtual memory is managed in Linux operating system. So, first we will see what this memory management is. So, when you are looking at memory management in the Linux operating system, it is categorized into two. One is the handling of the physical memory and second is handling of the virtual memory. So, when you are looking at handling of physical memory, it is allocating physical memory and freeing physical memory like the pages, groups of pages, small blocks of main memory. So, basically handling how space is allocated in the main memory and freed and so on. And the second category is to have this in virtual memory, memory is mapped into the address space of the running process. First we will see how this physical memory is managed. We all know that Linux is available for a wide range of architectures. So, for many architectures this Linux operating system can be used, and hence there needs to be an architecture which is independent of describing memory. So, Linux splits this physical memory into 4 different zones due to the hardware characteristics. They are called as zone DMA, zone DMA 32, zone normal and zone high memory. We will see what each one of these zones refer to. If you want to see the physical addresses of the different zones that is supported in that particular machine, we can use the dmasg the command. So, if this dmessage command is given after booting, it will show us the physical addresses of the different zones. So, now we will see one after the other the different zones, what each zone refer to. First is zone DMA, which is the memory in the lower physical memory ranges, and this is required by certain ISA devices. In the x86 32-bit architecture, some of the devices they will access only the lower 16 MB of the physical memory using DMA, and this region of the physical memory is called zone DMA. And memory in the zone DMA has generally been used by some specific devices. Say for example, they can be used for transfers with the network cards. The network cards can use only 24-bit addresses, and hence they can address only 16 MB, and those cards will use the DMA zone. Some cards or drivers they can access only or utilize the DMA zone. And the next zone called the DMA 32 is 4 GB in size, and this is used for data exchange with cards which can address up to 32 bits. But some devices, even though they support 64-bit addressing, they can access only the first 4 GB, and hence they will use this zone DMA 32. And the physical memory which is not mapped into the kernel address space is called the zone high memory. In the 32-bit Intel architecture, we see that 2 per 32 is 4 GB. The kernel is mapped to the first 896 MB of the address space, and the remaining memory is high memory, and it is allocated from zone high memory, and everything else is called zone normal, or the normal regularly mapped pages which are used by processes will be put into this zone normal area of the physical memory. And the memory within the zone normal is directly mapped by the kernel into the upper region of the linear address space. And many kernel operations can only take place using this zone normal, and hence it is the most performance critical zone. So, here we see that there are 4 different zones, but all architectures may not have all the zones. Some architectures will have only some of these 4 zones. Say for example, look at this modern Intel x86 64-bit architecture. It has a small 16 MB zone DMA, but the rest of its memory is called a zone normal. There is no high memory in this particular architecture. Look at this example of Intel 86 32-bit 32-bit architecture. Here you see that the zone DMA maps onto or refers to the physical memory which is less than 16 MB, and between 16 and 896 MB it is zone normal, and greater than 896 MB is zone high memory. So, thus we see that the main memory is divided into different zones, and depending on the architecture some of these zones or all of the zones are utilized. Now, each of these zones has got a list of free pages. So, the main memory is divided into zones and each zone has got a list of free pages. So, whenever a request for the physical memory arrives, the kernel will satisfy the request using the appropriate zone. And who does this? This is taken care of by a page allocator. So, the physical memory manager in Linux is called the page allocator, and each of the zones will have its own allocator. Multiple zones are there, each zone has got a number of pages, and the pages have to be allocated for requests from processes, and each zone has got a page allocator which does the allocation. So, what does the page allocator do? It will allocate and free the physical pages for that particular zone. So, it is capable of allocating ranges of physically continuous pages when there is a request, and this uses a method called the buddy system to keep track of the available or the free physical pages. So, we will now see what this buddy system is. When you have adjacent units of allocatable memory, those are paired together, and each allocatable memory region has got an adjacent partner which is called a buddy. So, whenever there are two partners or two nearby allocatable memory which are getting freed up, then they are combined together to form a larger single region, and it is called a buddy heap. So, the larger region also has got a partner with which it can combine to form a still larger free region, and so on. So, the adjacent regions are called as partners or buddies. So, when say two adjacent regions get freed up, they combine together to form one region, and if this bigger region also gets another adjacent region freed up, so that will also get combined to the big region to form a still more free region, still more larger free region. So, if there is a request for a small region and if that region size is not available, then what is done? A larger region is picked up and it is split into two partners, and those two partners are checked if you can allocate for the smaller request. If even if it is still larger, it will again be split into two more partners, but the splitting can happen till it goes to a size of a page, that is the smallest allocatable size is a single page. So, look at this example. See, there is a request for a 4 KB space and you have a large region which is 16 KB space. So, the 16 KB is first divided into two partners 8 KB and 8 KB, and this 8 KB, one of these two 8 KBs is taken and that is again split into two 4 KB spaces, and one 4 KB space is allocated to the request that is being asked by the process. So, here you see that buddy heap is split into two and that in turn is split into two, etc., and so on. Suppose if after the split happens, say you have 8 KB and 4 KB that is free. Suppose if the request for 12 KB comes, then this 8 KB and 4 KB will be combined together to form a 12 KB and that will be allocated. So, what we have seen now is allocating space in the physical memory when you have pages. Now, how is memory allocated for kernel data structures? We have been seeing in different modules earlier that there are a number of kernel data structures or a number of data structures that are maintained in the kernel, and these kernel data structures need to be allocated memory. Say for example, data structures like the process control block, the process table, VM struct, task struct, etc., and so on, and all these need to be allocated space. So, we see here that something called a slab. A slab is made up of one or more physically contiguous pages, and a number of slabs together form something called a cache. And there is a slab allocator which consists of a number of caches that are linked together on a doubly linked circular list called a cache chain. So, slabs put together form cache. There can be a number of caches which are connected using a doubly linked circular list called a cache chain. Now, why is this cache used? As I told you, this is allocating space for kernel data structures. So, for each unique kernel data structure, there is a single cache. So, if you are looking at inode data structure, for all inode data structure, you will have a cache, or you will have a cache for all inodes. You will have a cache for all file objects, etc. and so on. And each cache is populated with objects that are instantiations of the kernel data structure that particular cache is representing. So, if it is a cache for inodes, or if it is an inode cache, it will store instances of inode data structures and so on. So, you have multiple data structures, and corresponding to each data structure you have a different cache, and cache is made up of slabs. So, just look at this. There are two 3 KB objects that are mapped onto two caches, and the cache contains a number of slabs. So, slabs are made up of physically contiguous pages. So, now we will see how the slab allocation algorithm works to store kernel objects. So, when a cache is created, a number of objects are allocated to the cache, and the number of objects in the cache will depend on the size of the associated slab. So, if you have a 12 KB slab which is comprised of 3 contiguous 4 KB pages, it can store 6 2 KB objects. So, the size of the object is 2 KB, the size of the slab is 12 KB, and hence you can store 6 such objects in this 12 KB slab. So, the 12 KB slab comprises of contiguous 3 contiguous pages put together. Each will be of 4 KB size. You have a page of 4 KB size, 3 such contiguous 4 KB pages will be put together to form a slab. So, it will be of 12 KB size, and in this 12 KB size you will put 6 objects, because each object is of size 2 KB. And all the objects in the cache are initially marked as free. Whenever a new object is needed for a kernel data structure, say you need to bring in an inode, you need to allocate space for an inode, or you need to have a new object in the inode cache, then the allocator will check if there is any free object in the cache, so that you can allocate space for that inode using that particular free object. So, whenever a new task is created, say for example, a new process descriptor object has to be assigned, and then in that case it will check if there is any free object available. So, the cache will fulfill this request using a free slab, and any slab can be in one of 3 possible states. The slab can be full or empty or partial. Full in the sense that all the objects in the slab are marked as used. Empty means in the slab all the objects are marked as free. Partial means the slab consists of both used objects and free objects. Now, we will see how allocation is being done. The slab allocator will first try to find out, or it will try to satisfy the request with a free object which is present in a partial slab. So, if a slab is partially occupied, the slab allocator will first check into the partial slab to find out if there are free objects. If there are free objects, then it will use the partial slab to allocate space. If there is no partial slab, then it will look for an empty slab, and it will try to assign the object from the empty slab. So, if there are no partial objects, there are no empty slabs available, then a new slab is allocated from the contiguous physical pages, and it is assigned to the cache. So, now a new slab is assigned to the cache. So, already the cache has got some slabs which are currently occupied by objects, and hence there is no space for the new object, and hence a new slab is allocated to that particular cache, and memory for that object is now allocated from this newly allocated slab. So, basically why is this slab allocator being used, or what is the ultimate aim of the slab allocator? The slab allocator has got three principal aims. One is the allocation of small objects or small blocks of memory, so that you can eliminate internal fragmentation. Okay, so if it is a buddy system, the minimum size that you can allocate is 1 page, but now here you can allocate space for objects which are smaller than the size of a page. So, internal fragmentation is avoided. The second is the caching of commonly used objects is done. So, the system does not waste time allocating, initializing and destroying objects. So, if you have allocated some space for an object and if it is present in the cache, those can be used as such. You do not have to allocate afresh each and every time. So, benchmarks and Solaris system showed that there were a lot of speed improvements for allocation when the slab allocator was used. The third advantage is that the better utilization of hardware cache by aligning objects to the L1 or the L2 caches. So, now we have seen how this memory management is done in the physical memory. Now, we will see how virtual memory is handled, or management of virtual memory is done in the Linux operating system. So, the virtual memory, it will maintain the address space accessible to each process. It will create pages of virtual memory on demand, and it will manage the loading of the pages from the disk, or it will take care of swapping back to the disk as and when required. So, the virtual memory manager, it maintains two different views of a process address space. One is the logical view, which describes the instructions concerning the layout of the address space. So, what is this address space? The address space comprises of different regions which are not overlapping, like the text region, data region and the stack region, and each of these regions represents a continuous page aligned subset of the address space. And the second view is the physical view of each address space, which is stored in the hardware page tables for that particular process. So, here it is looked at as the process comprising of a number of pages, and the entries or the locations of where the pages are kept in the memory are entered in the page table. So, the pages can either be kept in the main memory or it can be kept in the disk. So, wherever it is being kept, that is maintained, or the location is maintained in the page table. So, this view looks at the process comprising of a number of pages. The other view, or the logical view, looks at the process comprising of a number of regions like the text, data and stack. So, there are several types of virtual memory regions. When you are looking at the logical view, I told you that you have the process being comprising of number of regions. So, there are different types of virtual memory region. So, the backing store will describe from where the pages for a region come from, and the regions are usually backed by either a file or by nothing. So, a region will have a corresponding information which is kept in a file, or the region can have nothing or can be backed by nothing, which is called demand zero memory. So, if the region is backed by nothing, whenever there is a request or there is a reference to that particular region, then a page will be allocated in which all zeros are being filled. So, when you are looking at a page or when you are looking at a region that is backed by nothing, what is given is a page filled with zeros. When you are looking at, or when the process is requesting for a page that is backed by a file, then that file's contents will be taken and mapped and be loaded onto this particular region or onto the pages of that particular region. So, a virtual memory region can also be defined by the way or by the region's reaction to the writes onto that particular region. So, again here we have two categories. A region can be a shared region or it can be a private region. If it is a shared region, then it means that the pages of the region can be shared by different processes. If it is a private region, then it means that whenever a process or whenever multiple people are trying to use that particular page, then a copy on write bit will be set, which means that whenever a process is trying to access that page, then that page will be copied and only then the process can write into that page. Just reading the page is okay, the pages can be marked as read only, but copy on write will be set. So, when a write is being done, the page will be copied for that particular process. So, when does the kernel create a new virtual address space? There are two situations. One is when a process runs a new program with the exec system call, and the second is the situation when the process is created using the fork system call. So, in the first case, during the exec system call, a new program is to be run. In the case of fork system call, a new process is just created which or may not run a new program. So, what happens when you are executing a new program as a part of this exec system call? The process is now given a new completely empty virtual address space. So, the virtual address space of the process which was there earlier is now totally erased and there is a completely empty virtual address space now. And if you give a program as argument to this exec system call, the file corresponding to that executable will be used and regions will be copied or pages will be copied from that file to this region. Now, this new process will get an entirely new address space or entirely new text, data and stack regions. So, the program loading routines will populate the address space with the virtual memory region. Suppose you are creating a new process with the fork system call. As I told you earlier, this involves just creating a copy of the process virtual address space. Say you have a parent process which is creating a new process using this fork system call, and the parent process takes care of creating a copy of the its virtual address space. So, now what happens, the child process also has got the same virtual address space as that of the parent process. So, the parent process virtual memory address descriptors, everything will be copied onto the new child process. But the new child process will have a new set of page tables, but whatever is there in the parent process will be copied to the page table of the child process. That means that the child is getting an exactly similar virtual address space as that of the parent process. So, the child, as I told you, the parent's page tables are copied into the child's page tables, but the reference count of each page alone is incremented, which says that why is this reference count incremented? This says that the child process is also using the parent process page. The page may not be copied, the same page can be used by the parent as well as the child process, or the parent and the child can share the same page, same physical page which is kept in the memory. Suppose if it is a read only page like the text region, a page of the text region, then that page need not be copied at all. The parent and the child can continue to share the same text page. So, if the virtual memory region is private, then in that case the pages for the regions are marked as read only and the copy on write bit is set. As I told you, if it is a text region, then in that case the parent and the child can continue to share the same region. But if it is a private region, say for example, if it is a data region, so the parent will have its own data. Now, when the child is created as a part of fork, if you are just if the child is not also going to use the same data region, what is done is that initially the copying of the data region is not done, but the data region is marked as read only and the copy on write bit is set. Now, say the parent is trying to write into that region first, then a copy will be created for the process which is trying to write and it will work on its own copy. and even if the child is trying to write into that page, write into that region, then a copy of that region will be created for the child process, and the child process will write into that page. So, till any one of the processes, the parent or the child, they try to write into that page, the page or the region will be shared by both the processes. Only when one is trying to write, a copy of that is made, and that is the use of this copy on write bit. Now, we will see what this swapping and paging refers to. See, the virtual memory paging system, it is responsible for relocating pages of memory from the physical memory out to the disk when memory is needed for something else. As we all know that there is no enough space for all the processes to be kept in the main memory, then in that case the pages, some of the pages will have to be swapped out to the secondary storage device and later be brought into the main memory when it is required. And here in Linux, there is no whole process swapping. This whole process swapping is an old method where entire process will be swapped in to the main memory and swapped out to the disk and so on. But now they are dealing with only sizes of pages. Only pages are being swapped into the main memory. So, individual pages only are moved. You do not move continuous or continuous big whole processes. So, the virtual memory paging system is now divided into two sections. One is the page out policy that needs to be used, and the second is the paging mechanism. What do you mean by this page out policy? Say whenever pages has to be written to the disk or moved to the disk. Say you want to bring in a page into the physical memory, but there is no enough space in the physical memory. Then you need to choose one page which is currently kept in the physical memory and move that to the secondary storage device. So, which page is chosen? That is, we have seen a number of page replacement algorithms in an earlier module. So, in the case of Linux, what is this policy? Which page is chosen to be moved out to the secondary storage device? That is based on this LFU principle, which is called the least frequently used method. So, this page out policy is very similar to this, the algorithm is very similar to the second chance algorithm that you had seen earlier, and it uses an LFU policy. And the second thing that needs to be taken care of in this paging is that the actual paging mechanism. So, the paging mechanism, it takes care of the actual transfer, it will page data back into the physical memory when it is needed. So, it will take care of the transfer from the physical memory to the secondary storage device and bringing back into the physical memory. Summary. So, in this module we learned how physical memory is managed. We saw that the physical memory can be divided into zones for better handling for different architectures, and then we saw the page allocator algorithm. Each zone has got its own page allocator which allocates memory. Then we saw this slab allocator which is responsible for allocating memory for kernel data structures, and then we saw how memory management is done for the virtual memory. We saw that virtual memory is divided into different regions like the text, data and stack. You can have a demand 0 region, etc. and so on. And then we saw that new virtual address space is allocated during a fork as well as during a exec. And then we saw details related to swapping and paging. When pages are swapped out, the policy that has been used for swapping out or paging out pages. The references. Thank you.